Anyway, I'll do this other side first.
Yeah.
Okay, welcome to the afternoon session. Should I be using the mic?
No, I think I'm good. No one can hear you.
Certainly can't hear you.
Okay, welcome to this afternoon session, which is going to be really exciting as this morning session and all other sessions during this workshop. And it's my great pleasure to introduce Chen Wang. We heard from him already yesterday, but we would like to hear even more. And he's going to tell us something about a potential revision to MPI-IO consistency and its impact on the HDF5. Please go ahead.
Thanks for the introduction. Hello, everyone. My name is Chen. I'm working at Livermore National Lab. I work with Harry and also Catherine. In today's presentation, I want to talk about MPI standard. The current MPI standard, especially its consistency design, consistency model, and some of the potential revisions we are trying to push to the next standard, and how those revisions gonna affect HDF5. So this is a collaboration with Catherine Moore and also my PhD advisor last year from UIMC, and I also want to acknowledge the MPI-IO working group, especially Quincy, who rebooted the IO working group. It's been dead for several years, and it's going right now. It started, the work group started regular meeting to we can revise the standard, part of the standard now. Yeah, so let's get started. So a little bit background on consistency model. I guess most of you are familiar with consistency model, consistency semantics. So essentially, a consistency model specifies a contract between the programmer and the system. So if the programmer follows the rules by the system, then the system should guarantee that the outcome is predictable. For example, think about a HDF5 program. So if you write an HDF5 program, you're going to follow the rules of HDF5. HDF5 is going to make sure that your data in the end is going to be correct. And similarly, if you are an HDF5 developer, for example, if you develop parallel HDF5 library, so you're going to use MPI-IO, so you need to follow the rules of MPI standard. Then MPI standard is going to make sure your code is going to be portable, correct, running on all kinds of different supported file systems. So within MPI-IO, there's different file system drivers. So MPI code can run on like Lustre, DPFS, or NFS, different file system drivers. So if you write correct MPI code, your code is going to be portable. So you don't really need to worry about the underlying file system. So in our work, in the world of storage, public consistency is the most straightforward consistency model. And it's essentially sequential consistency in the domain of memory. So we call it public consistency because it comes from the public standard. So it essentially says that after a write is successfully returned, all the subsequent read should be able to immediately see the update of that write. So it's very write is going to be immediately visible to the read. So there's a quick example with two processes, one write, one read. So the read is going to be able to see the write. If we are sure that the read happens after the write, we can use an MPI barrier, MPI send receive to make sure there's an order between the write and read. So the read can be seen. So the read will be able to see the write of rank data. So on the other hand, there's MPI-IO consistency. So it's not consistency. Here's a little bit of background on MPI standard. So first version of standard was published in 1994, and as a second version, we added parallel I/O into the MPI standard, which was published in 1997. So the young person was still decades ago. But since 1997, the I/O chapter of the standard hasn't been changed a lot over the years. So essentially, all the I/O calls we see today is essentially designed in 1997. So MPI standard doesn't provide sequential consistency like others. So it gives you a weaker model for better performance. So essentially, if you want to do read after write, you want to do conflicting I/O accesses from different processes, you cannot just use a single barrier to make that happen. You need to use MPI, which is called sync barrier sync. So you need to do an MPI file sync, and then barrier, then MPI file sync in between the write and read for this read to sync the update. So you need to use this special sync barrier construct in your MPI-IO code. So here's the HDF5 example. HDF5 doesn't have its own consistency model. HDF5, parallel HDF5 sits on top of MPI-IO, so it essentially provides MPI-IO consistency. So when you write a current HDF5, so you want to do read after write, or you want to do any conflicting IO accesses, you need to use H5 flush to get MPI barrier H5 flush. So it's essentially think barrier think, but here you use H5 flush. Flush is internally implemented using MPI file sync. So you can do concurrent accesses, but you need to make sure they are properly synchronized. Use this flush barrier flush using in HDF5. So when you look at a new consistency model, or when you try to evaluate assess existing consistency models, we can use the 3B criteria: programmability, portability, performance. So if you look at the MPI consistency model, that's pretty good. It gives you good programmability, it's very easy to use, and also gives you very good portability. It works on all systems that is supported. It doesn't have to be public system. It can be NFF, it can be Lustre, whatever system is supported. As long as it's right code. But the performance-wise, it's not very good. As I said, the standard 30 years ago. The performance-wise, it's not really good. We see some performance issues mostly because of this MPI file sync call. If you look at the standard, this is standard open one, this page 74, which talks about the MPI file sync call. If you read the standard, it says that this MPI file sync call will cause all previous calling process of this file to be transferred to the storage device. This essentially gives you persistency property. So guaranteed persistency, your data is going to be flushed to the storage device. It's going to be persistent. And it also requires all such updates become visible to subsequent read, which gives you consistency property. And it also requires this MPI file sync function to be a collective function. So you see, you probably already see the issues, the potential issues here. So first of all, it gives you two properties using a single call. You get both consistency and persistency, right? But in many cases, especially in the HDF5 cases, we only want consistency. We don't want to flush the data from buffer to disk. We want to keep it in memory. We make sure it's consistent. We don't want to flush to disk because that's going to be expensive. So in many cases, we want only consistency. We don't want persistency at all. So it's an overkill that this function guarantees two properties at a single time. Secondly, it's the granularity. So this MPI file can synchronize the entire file, which may not be necessary. But sometimes you just update a subset of the file. You want to, for example, the beginning, the header of the file is metadata. You want to update, make the header of the file consistent. You don't want to flush the entire data. You don't want to synchronize the entire file, right? So the granularity here is another concern. Third one is collectible. This can be a big issue. So currently, the standard requires MPI to be a collective, meaning that if you have a million processes opening the same file, when at the time you call MPI file sync, everyone has to call MPI file sync. You have to wait for everyone to call this function. So it's going to be a barrier point. But in many cases, what we found is that only a subset of processes actually are talking to each other in terms of I/O. So there's probably one process as a producer, then another two processes serve as a consumer. So only the three processes need to call the same call. You don't want a million processes to call this because it's going to give you, it's going to have some straggler issue, especially if there's some compute, and then you need to wait for the stragglers. So it's really expensive to be a collective. And finally, the current barrier safety design is not able to actually write who's the producer, who's the consumer, who actually writes data, who actually reads the data. It's just think barrier thing. Both the thing function called R and PI file sync. So there's no way to tell who writes it. So it reduces flexibility and also needs for optimization and library. So what we can do to get around this issue, to solve this file sync call. So people have been doing different things. Here is one common strategy people are doing. So on the left is a factor. If you want to do read after write. On the left is a factor. You do a flash, you do H5 flash, and the barrier H5 flash. On the right is incorrect code. You can just ignore the MPI file flash. It's still going to work correctly on POSIX file systems. Why? Because the write function on POSIX file systems is already strongly consistent. You don't really need this MPI file sync or H5 flash to make it work. So on the other side, on the other hand, the incorrect MPI code here can reduce portability because it is not guaranteed to run on non-POSIX file systems. It will work on POSIX file systems, gives you good performance because you ignore MPI file sync, but it's not guaranteed to run on non-POSIX file systems. Like NFS or any new file systems that are non-POSIX. There are many new file systems that are non-POSIX that MPI can support. So the same HDF5 code is going to break there. So, for example, within MPI-IO, you could have NFS, UFS, which provides different consistency models. So the point here is that portable HDF5 code or portable MPI code should not make any assumptions on the underlying file system. You just need to write the correct code, make it portable. You should not make any assumptions on the underlying file system. Because the MPI standard doesn't say anything about underlying file system. As long as there's a working driver within MPI, it should work. You should not worry about the underlying file system. Just like if you write a C code, Java code, the compiler is going to handle everything for you. You don't need to worry whether it's IBM, CPU under the hood, or it's Intel IBM CPU. So similarly, if you write HDF5 code, you should not worry about the underlying file system. You can do specific optimization. In terms of correctness, you should not worry about underlying files. Just write the correct MPI. We actually designed an algorithm to check whether it is correct according to MPI standard or whatever standard. We actually found that within the latest HDF5 source code under the task parallel code, there's 7 tasks not correct according to the MPI standard. I think you're doing that on purpose to boost performance, but those tasks kind of fail on non-POSIX files. Okay, so what is the better solution here? So remember, the fundamental issue here is that the current MPI standard has some issue with this consistency design. It provides a single function called gives you both persistency and consistency. So there is no function, no MPI API for consistency only scenarios. I think this is a overdue function that we need to add to the standard. So we want to introduce probably 2 new MPI functions that are dedicated for consistency only scenario. And those functions are going to have zero cost, nearly zero cost on POSIX files because POSIX file is already strongly consistent. So the new function is going to be zero cost. And application like an IO library should be able to use those new functions, have new cost on POSIX system, and their code is going to become correct for all file systems supported by MPI. So there are many decisions to make if you want to introduce new synchronization functions to MPI standard. This is the issue I have shown for MPI file sync, the same decisions you need to make for any new synchronization function. So for example, you want both consistency or persistency. For this scenario, we only need consistency. Granularity, do you want to synchronize an entire file or subset file, collective or non-collective? Whether you want to be able to recognize producer or consumer, or it's just a single call. So many decisions to make. So we proposed a few different alternative revisions or designs and show in the next few slides. So the first is just introducing a single function, MPI file flash. This name has not been used in the standard, so we could use this name, MPI file flash. So it's essentially MPI simplified version of MPI, just removing the persistency part of MPI, guaranteeing only consistency. And this function is again a collector. So instead of doing sync barrier sync, now you can do flash barrier flash to make sure the code is correct. This is the first design. Second design, introducing 2 function calls, MPI flash, MPI refresh. So flash is going to be called by the producer, fresh is going to be called by the consumer. So the new construct becomes flash barrier refresh instead of previous sync barrier sync. So it's going to be flash barrier refresh. And both calls, we make both calls non-flexible, meaning that only the relevant IO all those functions, not the other possibility. If you open the big file with only the consumer needs all the functions. You don't need to wait for everyone. There are going to be no standard issues at all since they are non-flexible. Finally, the last design. If we wish, if just the previous design probably adding some more finer granularity, we introduced probably two more functions that accept a subset of the file, a range of the file. So you could make a subset of file consistent. You could pass in the range, not the entire file. So this provides more flexibility, but reduces programmability actually. But this is just a more flexible API. So here's the quick summary of the three possible designs. Okay, one is just using a single MPI flash, which is maybe the most easiest one to give static to be a static. Second one is file flash plus file refresh, which can be used. I think it is the second one. We choose mesh better with our starter system. So we are thinking right now something we want to push to the standard, right? We are thinking about how this MPI, how the new standard can support future systems. I think future systems need two calls, need to be able to distinguish between producer and consumer to achieve better performance, to do more optimization. And I want those two calls to be non-reflective, so you don't really need to block their better. If we give more flexibility, we introduce four calls, which you can make subset file consistent in not another entire file, but of course it's add more cost to it's reduces programmability. Okay, so how many?
Five to seven.
Okay. So current data. So I've been discussing this potential revisions within the MPI working group. I'm currently preparing for the revision draft. We need to bring this proposal to the MPI voting committee to vote to make it happen, right? So I also did implementation work to make sure that everything works fine. I implemented those two functions, MPI file flash and MPI refresh within MPage and MWebPage. I did that for both lecture, GPFS, UFS, driver. They are essentially no up within public file system, so very easy to implement. And we are pretty sure that this will never hurt. Going to be improving your performance without any issues, because there's no law, right? And make sure your code can be fun. And I also added a new driver for UFF, which is a non-public file system, to demonstrate the benefit of this new API. So in terms of data, I'll go to this slide first. In terms of performance, so you will never get that performance because it's just no up on public file systems, so you're gonna get portability performance at the same time. So this is a quick experiment on 16 nodes with 4 megabytes. I also using on the right, you could see different file systems here. So it's gonna save you synchronization time because again it's no up compared to the previous sync area. I think it's no up, so it brings down the synchronization time to basically 0. So it's in all different file systems we tested, it's cut down the to at least by half. And this is large I/O. If you do small I/O, the improvement can be even bigger. And more importantly, if your application have compute, you could very likely to experience better issues with previous design barriers. If you use the new APIs, you won't have any stragglers. It's further improved here. So anyway, so what is the impact on HDF5 and also the other libraries? So current design, current MPI standards still, right? Sync barrier sync still work, so existing code still gonna work. But when available, when these functions are added to the new MPI standard, HDF5 or other libraries could take advantage of those new APIs in these scenarios. to improve performance because you don't want to flash the disk, right? And with the new APIs, it's really hard to correctly use those new APIs because it won't hurt your performance. It's just no off on hard disk file system, and your code can run correctly on hard disk file system as well. So just don't ignore correctly. Some other opinion is HDF5 is possibly can introduce new calls like H5 to take advantage of new API to kind of like condense the three calls within a single H5 fence. So for users, users do H5D write, H5 fence, and H5D read. Inside of HDF5 library, you can do a lot of optimizations within this H5 fence. For users, there's really nothing need to be done. You don't really need to change your code. But when a new API is available, you can try the new API for better performance, especially for consistency only scenarios. Okay, so that's it for server. I hope to bring this to vote in the near future. I plan to evaluate the performance improvements on all this kind of the real applications. I'm thinking about designing a new algorithm to check for unnecessary initialization calls. We have an algorithm to check carefully if your code has enough initialization calls, but I also want to check if your code has too many initialization calls. It's going to hurt your performance. Okay, with that, I off my time today. Yeah, we have done some prior work lead to the proposal, so I put the references here.
Thank you. You are facilitating. I think we have time for one question.
With flush said lower number of ranks is not a problem, but when you start to get into exascale, and all the ranks are calling it by flush, that means they all pound the file system all at once.
Yeah.
You can hurt performance quite a bit. But do you see a way around that?
Yeah, with the instruction calls, you don't really need to call H5 flash from everywhere. You only need to do you only need to call it from the ranks that try to make data visible to others. You don't really need this because the new proposed API is not flash. You don't really need to call it from everywhere.
You can kind of stagger it too, right? You can have a certain number of ranks to call a flush and then have you can stagger out the I/O.
Yeah, you could do that actually. Yeah, because it's not vector. You don't need to wait for everybody. You don't need to call it all together. You don't need to issue a million flash.
Fantastic. Let's thank our speaker once more.